Hi, this is Dr. Maria Weber, and our next mini lecture is about power, in particular, electrical power and electrical energy. Electrical energy and power. Electrical power represents the movement of charge through a voltage per unit time. The energy that is expended is the electric potential energy, and that is equal to our charge times our voltage, which we learned before spring break. So our power, remember that power is equal to an energy over time. So we learned that last semester. So power is equal to our potential energy divided by time. So that's equal to our charge times the potential difference, or the voltage divided by time. Now, remember that current is also Q over T, or delta Q over delta T. So this power is also equal to the current times the voltage. So using Ohm's law, we can rewrite this equation in a couple of different ways here. So we have the first one, still power is equal to current times voltage. Remember that voltage is equal to current times resistance. And so we can rearrange that in two different ways to say that power is equal to voltage squared over the resistance. It's also equal to current squared times the resistance. So to get this last one here, we replace V with IR. So then we would have I times R, so that's I squared times R. Now for this one here, if V is equal to IR, then I is equal to V over R. So we replace this current with a V over R. So we have V over R times V, so then that becomes V squared over R. Now, power has units of watts. Electrical power has the same unit as the power that we were talking about last semester, which was like mechanical power, units of watts. And the unit of energy used by electric companies to calculate energy consumption is the kilowatt hour, which we represent as K big W times H, kilowatt hour. So over here, we could solve this equation and say that energy is equal to power times time. And so an electrical company would calculate that energy that you've used in your home with the quantity or the unit of a kilowatt hour. All right, so just with these simple ideas here, we are going to solve one problem. We're going to think about the cost of lighting up your life. So we have a circuit, and it provides a maximum current of 20 amps at an operating voltage of 120 volts. Part A, how many 75-watt bulbs can we operate with this voltage source? And for part B, at 12 cents per kilowatt hour, how much does it cost to operate these bulbs for 8 hours? We're going to apply the electric power concept and calculate the cost of power usage using kilowatt hours. So we have a circuit which provides a maximum current of 20 amps or 20 amperes at an operating voltage of 120 volts. So for our first part of this problem, how many 75-watt bulbs can be lit up with this particular current and voltage? Well, we can look at our equations for power. There's a couple of different formulations, but in this case, we're given a current and a voltage. So our power is just going to equal to I times V, our current times voltage. And so that's just going to be equal to 20 amperes times 120 volts. And so then we see that the power required to light up, or the power that we can get to light up these bulbs, is just going to be 20 amperes times 120 volts. So 2.4 times 10 to the 3 watts, or 2,400 watts. So that's the power available to us. And how many 75-watt bulbs can we light up with this amount of power? To find our number of bulbs, we just take the total power and divide it by the power required per each bulb, okay? So if we do that, then we've got 2.4 times 10 to the 3 watts divided by our bulbs. Each bulb consumes 75 watts of power, and so that's going to tell us, if we take 2,400 divided by 75, that we can light up 32 bulbs with a 2,400 watt power supplied to us if each bulb has a wattage of, requires a wattage of 75 watts, okay? Now for the second part of our problem, we want to find how much it costs to operate these 32 bulbs for 8 hours. And we're also told that per kilowatt hour, which is an energy usage number, per kilowatt hour we're charged 12 cents or $0.12 per kilowatt hour. So this is an energy rating, okay? So in order to find how much it costs per kilowatt hour, first we have to figure out how much energy is being consumed by these bulbs in units of kilowatt hours. So we know from last semester that power is equal to energy over time. So if we're looking for energy, we have that energy is equal to power times time. And the power that we're consuming is this 2.4 times 10 to the 3 watts. And we're doing this for 8 hours. So I'm going to multiply that by 8 hours, okay? And so my energy units that I'm looking for are in units of kilowatt hours. Here I'm going to have units of watts times hours. So I'm going to use a conversion factor to convert these watts into kilowatts. And so we recall that there's 1,000 watts in 1 kilowatt. So I'll just have to divide 2.4 times 10 to the 3 times 8, divide that by 1,000 in order to get our answer in kilowatt hours. So, oh, not kilometer here, this should be kilowatt, okay? And so if I do that, then I find that our energy consumed is 19.2 kilowatt hours to run those 32 bulbs per 8 hours. Now the cost to run those bulbs for those 8 hours is going to be our 19.2 kilowatt hours times the fact that we're charged $0.12 per kilowatt hour. Okay, and so my kilowatt hour units canceled, and so the amount that I'm charged for these bulbs for 8 hours is going to be 19.2 times 0.12, so $2.30 to run all those light bulbs for 8 hours. So you can think about that as being maybe like a small office building. Maybe it has somewhere around 32 light bulbs in the small office building, and to keep it open for around 8 hours costs about $2.30 per day. So let's talk about some lessons we can learn about power and Ohm's law from filament light bulbs. Here's an example of a filament light bulb. You still might have a few of these around your house. Inside here, well, current is flowing inside here, and current moves or flows through a piece of wire here made up of a metal called tungsten, and that tungsten gets so hot that it glows, it lights up, and that's what creates the glow from a light bulb. Okay, now you might notice this, that as filament light bulbs age, they tend to give off less light. So the high temperatures inside this light bulb here evaporate tungsten from the filament, and that decreases the radius of the tungsten filament. So this decreased radius leads to an increased resistance. So remember, we can have an equation: resistance is equal to the resistivity times the length divided by the cross-sectional area. So if that area gets smaller because of a decreased radius, then our resistance increases. Now, we have Ohm's law. Voltage is equal to the current times resistance. So voltage stays the same, but the resistance is increased. So that means that our current that's running through our light bulb is now decreased. So that diminishes the amount of light given off by our light bulb. Also, this tungsten that's been evaporated also coats the inside of the light bulb, making it a little bit more opaque to this light coming through. So those are some reasons why filament light bulbs tend to give off less light as they age. Now, you might also notice that if you still have these filament light bulbs, which we also call incandescent light bulbs, you might notice that they often will fail right after you flip the switch, right after you turn them on. You might hear a popping sound or something like that. So as the filament warms here, the resistance increases, the, and as this resistance increases, the current decreases moving through our filament. And as that happens, the power delivered to the bulb also decreases, but the voltage applied remains constant. Now, the resistance of the filament is lower whenever it's turned on because it's not as hot. That leads to a higher current and a larger amount of power delivered to the light bulb when you first turn on that switch. And that current spike is what tends to cause light bulbs to fail in the first place right after you flip them on.